Thank you. Can everybody hear me okay? Yeah, we're good? Okay. Thanks. As he said, my name is Jeremy. You can catch me on Twitter and GitHub at that handle there. It also works for Gmail, words I may live to forget, but go ahead and hit me there. By day, I'm Director of Platform Engineering at a company called Acuity, which is headquartered in Toronto, Ontario, Canada. We're a retail analytics company, which means we're a little bit like Mint.com. So we take store-level data for retailers and their suppliers, get them on the same page, and help them make data-driven decisions to improve their business. Our backend is a mix of Erlang and Scala, and we are, of course, hiring. So if you like things like Canadian companies or ETL and OLAP problems that are multi-tenant, please come talk to me. But we're really here to talk about Alpaca. So, in brief, Alpaca is a statically typed functional programming language for the Erlang virtual machine. It is written in Erlang so far and compiles using the core Erlang AST and compiler module. So that's just the core module if you're familiar with any of this stuff. Comes in your standard distribution, no big deal. As much as possible, we want to interoperate safely with Erlang and with the rest of the Erlang ecosystem. And that last point does have a couple of implications we'll get to later, specifically when we start to talk about the trade-offs that we make. So in terms of syntax and features, Alpaca is heavily inspired by the ML family of languages. So if you have experience with things like either OCaml or Elm, some bits of this are going to look eerily familiar, but not exactly the same. I started working on it in January of last year and open sourced it in June. So we're still pretty early on, but it's already useful for a few things already, and you can generally use it for a variety of problems. Something that's probably pretty important to mention as well is that our type checker prioritizes being able to infer types rather than requiring type annotations explicitly. At present, we don't even have annotations, although that is coming. The typer just tells you when you've mixed something up. So if you try to add an integer to a string, that's going to be a compile time error right out of the gate. And finally, while we are ML inspired, we're not intended to be ML. So we're prioritizing being functional and statically typed over replicating any of the usual suspects entirely. We'll shamelessly take any good idea, but I don't really want to be dogmatic about which one of these things we consider to be the one true language. I don't think that's a useful fight to wade into. And right now, we don't care about things like higher-kinded typing or dependent typing, effect typing, any of the ad hoc polymorphism flavors. All of these things, I think, are important for us to deal with at some point. But we're really trying to be conscious of prioritizing more basic features and functionality ahead of time. So things that make us really useful, again, within the Erlang ecosystem. It should be noted we don't even have, if you're coming from ML, we don't even have like an ML module system right now at all. We've talked about it, but right now Alpaca modules and Erlang modules are one-to-one correspondence. We don't really do anything fancy there at all. And when I started working on what became Alpaca, I had absolutely no idea how Damas Hindley-Milner worked at all, had no idea what type reconstruction was. There's a whole other talk buried underneath this one about how our typer works in a lot of detail and where to start if you want to do something like this, because it is a very tractable problem. But this is not that particular talk. And my objective today is to give you a flavor of where Alpaca is coming from, why it exists in the first place, what's already working, and where it still has some problems that we need some help solving. I'd like to encourage all of you to come and participate in Alpaca's development. To that end, we'll talk a little bit about the community and how that's structured to wrap up this talk. But let's start with why even build something like this in the first place? What's the motivation? Well, I started working on Alpaca initially for two reasons. I really like Erlang and its virtual machine. But I also love being able to rely on static typing for faster iteration, which is going to be a controversial statement, I understand. But in my experience, a decent typer can help to reduce, not eliminate, but reduce the number of tests that we have to write, especially the upfront tests. So in addition to Erlang, as I mentioned, I spend a lot of time in my day job in Scala. And so some of the motivating bits, especially around typing, come from things like Scala's case classes, this kind of example. I really like case classes in Scala. I like the way they let me model code and think in terms of relatively expressive types. I think of them a little bit like type constructors in an ML language coupled with records. So I sort of think of case classes as a stricter version of that coupling. So here we have something that looks a little bit like OCaml's tag variants and records. Elm, I think you can do exactly the same sort of thing. And this happens to be perfectly legal Alpaca code as well. You can drop this into the shell that we have or an Alpaca module and it'll work no problem. But the problem is that in Scala I can't use patterns everywhere like I can in Erlang or in ML. So I can't destructure case classes in a function head like this. And that frankly makes me kind of sad, because this sort of shorthand I find both expressive and very useful in Erlang and in ML variants. And when I'm moving between Scala and Erlang, tests are another particular place where I think Erlang's approach really shines. I like how eUnit lets our tests live right beside the code that we're testing. And the distinction that we have between eUnit and common test is really nice. I know that not everybody likes one or the other, but the fact that we have two very coherent approaches to different styles of testing, and then layer on quick check or proper on top of that, is kind of amazing in our industry as a whole. And unfortunately, testing on JVM languages is typically nowhere near as simple. You know, we often need completely separate source trees, completely separate test classes, just to check what we're doing with our code. We don't get that same kind of flow. It's not really possible where you can have your tests and code living beside each other. I think having tests live beside the code that they're testing is also a really great set of examples. So when we're coming back to something we wrote a year ago and trying to decipher what we did, it's really useful to have that right beside each other, right? Or if we're coming to somebody else's code and trying to figure out what they've done. So we do try to steal a bit directly from Erlang with Alpaca. And because I think Erlang does tests and pattern matching particularly well, Alpaca tries really hard to keep both of those things front and center in its design. From very early on, it was important to me to be at least as test-friendly as eUnit is. And again, to me, that means being able to couple tests and the code they're testing together in the same file. And this tension between the two languages, tests and pattern matching in Erlang versus modeling and typing in Scala, is a large part of why I started what became Alpaca in the first place. One of the very earliest motivating bits was actually case classes and the type checking that comes along with those. And the tools that we have to model our problems and solutions aren't strictly part of type checking, right? Like case classes, type constructors, records, those kinds of things aren't necessarily only strictly coupled to type checking, but I think it's all really connected. I generally think of the type checker as a free set of tests, especially when we include pattern match exhaustiveness checking. It's all, in effect, a low-cost chunk of test-driven development to me. And unit and integration tests then themselves become more of a behavioral set of tests. That's really what we're checking there, right? And this is where things like in other corners of our industry, things like dependent typing or closure specs start to look really exciting as well. The key here, though, is that I think tests, or test writing, I should say, and type checking are really two sides of the same coin. I don't think we should have to pick one or the other. And types and tests are not in competition. They're not in opposition to each other. They can and should support each other. And I want to work with a language that actually considers both of these things to be first-class citizens. I don't see why we shouldn't have that as a first-class construct, both of them. I also really want to make tools like Alpaca accessible for other people. I think this combination of test capabilities and type checking can actually provide a competitive edge, and I'd like to share that. I think that if more of us have that, we'll build better stuff together, and I think that's a win for anybody. And it all basically translates to, I wanted a reasonably pragmatic, statically typed language with algebraic data types, lets me pattern match everywhere, and which easily integrates tests, which is not at all a tall order, right? So, for those of you who haven't tried Alpaca yet, here's a sneak peek. We have pattern matching in function definitions here with map. I don't know if everybody at the back can see that, maybe a little bit tiny. But the pattern matching in function definitions is much like you might do in Erlang, and an associated test. There's a pretty basic algebraic data type here, the option type, or if you're in Haskell, the maybe type. I think that's what Elm calls it as well, but I'm not sure. The map function is basically a functor map. I think some languages call this fmap. It's not flat map. It's very different. But the basics are that, you know, if we apply map to an empty option, we get an empty option at the other side. We don't even talk about the passed-in function. Don't care about it. And if we pass a non-empty option with something in it, we get a new option with the function applied to the contents at the other side. As you expect, the type of the resulting option depends on f. So if the function we're giving to map is integer to string and we give it an integer option, we get a string option at the other side. Note that assert equal in this test here is not strictly part of Alpaca, but it's pretty easy to define. Tests in Alpaca get synthetic names that match the way that eUnit names its tests. So if you're using the rebar3 plugin that Tristan wrote, you can bang rebar3 eUnit into the console, and your Alpaca and Erlang eUnit tests will run in the same go. There's no changes you have to make there. Pretty straightforward. And here's a quick and dirty assert equal definition. if you're curious about how that might look. This is a type-safe assert equals. So if you hand this an integer and a float, you're going to get a type error. It won't even go to tests. But otherwise, it does pretty much what we want. If A and B match, then it just proceeds and the test passes. If they don't match, it throws an exception, and eUnit will tell you your test failed. Basic. So before we actually get into the details of Alpaca itself and some of the core features, I want to talk a little bit about some of the key principles. And there are 3 key principles that we keep in mind while building Alpaca. And the first thing is type safety, which I know I've banged on a bunch about, but we'll talk more about anyway. Type safety is prime. We want to be able to model and specify our intent, and Alpaca should check that model for us and tell us if we got it wrong. That's really the goal here, right? This includes things like pattern match checking for exhaustiveness. Well, something that's still fairly in the early stages for us, but it already exists for top-level function definitions. So if you're doing pattern matches in function heads, Alpaca is going to yell at you if you didn't actually cover all your cases. The second thing is basic utility. How useful is Alpaca? Can we write useful programs with both Alpaca and other languages in the Erlang ecosystem? Does it make it simple to test those programs? That's a key part of usefulness as well, I think. And the last principle is simplicity. A simple language to me is one that doesn't require a lot of memorization or recall. It should be as obvious and consistent as possible, rather than being implicit or cryptic and having to decipher things. I think that we need to be guided by a relatively simple set of questions for this too, like how much of the language itself is implicit or hidden? How many competing or contradictory things do we have in the language? How much of the behavior and the semantics of the language are obvious, from what you're seeing, rather than how much do you kind of have to force yourself to remember and figure out what's actually happening? Occasionally, we will trade some of these principles off against each other, and you'll see examples of that. But for the most part, you'll find that type safety really rules everything, followed closely by the broad utility or usefulness of Alpaca within the ecosystem as a whole. And to double down on an earlier point, this means being as friendly as possible with respect to Erlang or ecosystem interoperation in general. So just the last thing before we get into the specifics of the language, I want to talk a little bit about 2 things. Why we target the Erlang VM and why we're basing things on the ML family of languages in particular, because that's a completely different syntax too, right? To start with, why Beam? Why the Erlang VM? And there are 2 main reasons. The Erlang VM itself and core Erlang. So as far as the VM goes, I really just like the properties we get with it. We get the basic soft real-time stuff that the previous speaker talked about, but we also get great debugging and tracing facilities. And lots of guarantees are baked right in there for us, like all the message passing stuff and message receiving. All of that stuff is done and with very well understood properties already. And core Erlang, similarly, makes a bunch of things relatively easy for us to do. A lot of the basic constructs and key abstractions are right there in its AST. We don't have to do a lot of the heavy lifting that you would normally do with a new language. I think there's probably a subtle reference to definitional interpreters under there, but I won't get too into the weeds there. As for the ML family, I really like its brevity. There's really no ceremony about braces or parentheses, and it's very expression-oriented. I think that expression-oriented nature helps to make us think about things from more of a compositional perspective. And that's not to say that Erlang doesn't force us to think about things from a compositional perspective as well, because it clearly does. It's more that, Erlang aside, I think ML is a little bit better of a place for us to be pulling things from than other languages in our industry. Now, I'm likely going to mention the terms unification or unify a few times as we get into the details here. So for the purposes of keeping things simple, you can treat those words as meaning, given 2 expressions, can we show that they are the same type? Anybody who's an expert in inference or type reconstruction, I'm sorry, I know it's a gross simplification, but it'll work for today. So let's talk about a few differences and similarities to get started. The biggest and really only breaking differences are that strings are UTF-8 strings, or UTF-8 binaries, I should say, like in Elixir, and records are compiled as maps instead of as tuples. And there are a few reasons for that, and we'll get into the why of that later. Maps and lists in Alpaca are just Erlang maps and lists under the hood, but they are typed with parameters. So if you were coming from the ML side of things, we would talk about parametric polymorphism. If you're coming from the Java side of things, we would talk about generics. I'm just going to use generics because it's easier for me to not mess up through the body of this talk. So here's a basic map with atom keys and string values. Nothing particularly strange here. We use Elixir's atom syntax just to keep things clean between variable and function names as well. And here's a map that's going to give you a type error. So all the keys in a map have to be the same type, and all the values have to be the same type as each other as well. So you can have a map from atoms to strings, but you can't have a map necessarily from atoms and integers to strings, right? We have both sum and product types. So this is a pretty obvious tuple, one of our product types, and a specification for that same tuple type, if you wanted to specify this as a user-defined ADT. Records are the other kind of product type, and we'll get into the details of those shortly too. Sum types, or if you prefer union types, are pretty straightforward and play well with generics, as do our product types. So we could have used type variables on the previous slide. We're borrowing OCaml syntax here with the apostrophe for type variables. And we do allow for recursive types too. So here's the obligatory linked list example. It might be a little small for the people at the back, but we'll carry on. Type constructors take a single argument, which I think is pretty common in most languages. Here we're using a tuple to cons. We do use the literal tuple syntax rather than using asterisks as you find in other languages. I think it's a little bit more straightforward. And here's an ADT that on the face of it looks a little bit dangerous. We're unifying integer and float without type constructors, right? How are we going to tell the difference between these two in a match? Or how are we going to tell the difference between this and an integer in a map? So those of you who are familiar with type inference will note that we are breaking decidability here. Alpaca, when it sees an integer in the presence of this type, can't tell whether it's an integer or this particular type. There are a couple of rules it goes through to get there, but this is really key to how Alpaca wants to be friendly with other languages on the Erlang VM, because these kinds of unions are normal for us to work with, but still maintain type safety for when we're purely in Alpaca land. And the way that we type pattern matches plays a really big role here. And just before we talk in detail about matches and clauses and what that means for typing, I have to admit to something up front, really. The any type, I don't really like it at all. So this is where you mix integers and floats in something like OCaml or Scala, and the compiler just tells you, well, that's the any type now. I can't figure it out. I really don't like it. I'd go so far as to say that I hate it. So you cannot explicitly use the any type in Alpaca at all. If you mix a float and an integer, you won't get any out the other side. Alpaca will tell you you screwed up. Unless you have an ADT in scope, but again, we'll get to that. So let's build up to how we work with that previous union by looking at matches in some detail. Here's the form of pattern matching you're used to in Erlang with case of, right? And like in Erlang, it looks pretty much the same if we're dealing with receiving messages, and we use the same form for our foreign function interface, or FFI, as well. We can also apply guards, as we do in Erlang. So here we have an integer guard, so x has to be an integer. We haven't implemented every single type check yet, but they're pretty easy to add. So if you're looking for low-hanging fruit, you can come and help out with that. Guards right now, you can have multiples separated by commas, but they all have to evaluate to true. It's all conjunction, conjunction. We don't support disjunct or ors yet. There's no reason we can't. We just haven't gotten around to it yet. So this match here in isolation, that unions integers and floats, is going to be a type error, right? Alpaca will not let you mix those just implicitly. You can't just get an any out the other side of this. Patterns all have to unify with each other, so the patterns all have to be exactly the same type, and the bodies all have to be exactly the same type as well. But we can fix this by bringing the ADT in from before. So this is that union type where we're doing the dangerous union of integers and floats. Right? Again, we want to be able to work with the exact same unions that we are able to in Erlang or Elixir or anything else. And let's work up to how we actually type that. So here we have a really simple clause, this pattern match, where we have an integer pattern and an integer body. Now, Alpaca knows that the body is an integer and that x is an integer because plus can only be applied to integers. If you try to add with plus 1.0 and 1, you're going to get a type error. If you want to add floats, you have to use plus period like you do in OCaml, let's say, right? So Alpaca can pretty easily tell that x should only ever be an integer. But what happens if Erlang calls this with a string, right? There's no way that anything outside of Alpaca is going to know what we're going to permit with Alpaca here. Alpaca is not going to let us call this with anything other than an integer, but Erlang or Elixir or LFE can shove whatever they want into this function and we won't be able to stop it. So in Erlang, with a forced or contrived example, we might throw up a type guard on here, like we've already talked a little bit about, right, to catch that and avoid the bad arithmetic exception. Alpaca lets us use pretty much the same functions as you saw, but in Alpaca they do double duty, both as guards and as additional information for the typer. We kind of privilege guards. So back in Alpaca, we can include a type check that not only guards us at runtime, just as we're used to in Erlang, but it also serves as additional information for Alpaca's typer. We don't throw that information away. We privilege these particular functions. As an aside, for those curious, these guard functions in Alpaca compile to the same Erlang functions, and guards have the same restrictions as we have with Erlang guards. We haven't changed anything there, really. So if we drop the addition bit, right, which means that we remove that information for Alpaca to see that it's an integer, this guard gives us the runtime checking that we're used to, but it also informs the typer. We don't throw that information away. We use that information to feed the inferencer, okay? And it's crucial to how our foreign function interface works as well. Now, to be a little bit more specific, or to double down again on an earlier point, in Alpaca, we want to be able to work with the union types that we're used to in Erlang. We don't want to throw that stuff away. We don't want to make that hard or make anybody jump through additional hoops, or at least too many additional hoops. Type guards let us maintain all the runtime safety we're used to, but we also leverage it for compile time checking, the type checking as well. We don't throw the information away, okay? So expanding on this, all calls made to languages in the Erlang ecosystem outside of Alpaca must go through the FFI. So here we're calling Erlang date, right? You can't call Erlang.date from Alpaca. It'll tell you that it's not a defined function. You must go through the FFI. And this isInteger clause here is even more important because it's the only way that Alpaca knows you're giving it a tuple with 3 integers coming out the other side of this, right? It's the only way we're actually going to be able to tell anything. And to reiterate, again, these guard functions can be used anywhere you normally use clauses. So you can use the same guards in message receives, you can use them in FFI, you can use them in normal pattern matches. We can also get really simple if we want to. So here's a trivial function to print a simple greeting or message. And you'll note that in the pattern, we're not even bothering to check the type because the body is always an atom. So Alpaca can tell really easily that an atom is always going to come back from this function. No big deal. In general, it's pretty easy to kind of cobble together functions with our FFI to take advantage of all the libraries you're used to. As an aside, if you can see, notice we're matching on the type of X here, right, with this is string. And the reason we're matching inside Alpaca, not in the FFI, is because the foreign function interface doesn't type check any parameters going into it. So anything in that list of parameters you pass to a beam call is not type checked. We don't care what it is. We don't want to have to unify all that stuff. We assume you know what you're doing. So if you want to restrict this to strings, right, on the way in, you have to type check in advance. So Alpaca, you have to give Alpaca a little bit more information as to what's happening. It's important really to be as specific as possible. Okay, so enough of the basics. The parts that I really like the most so far in Alpaca are typed messages and records with row polymorphism. To simplify that last bit, our records should feel really familiar to anybody coming from either OCaml or Elm. We have a few extensions, a few differences here and there, but they're pretty close. So usually the first thing people ask me about Alpaca is, what about typing processes and messages? And the short answer is that all message sends in Alpaca, within Alpaca, are type safe. They are checked at compile time. So let's look at a simple motivating example before we get into the basics of how that works, because I will explain why. So here's a really simple example of a process that we're going to cause some problems for. On the top, we have an adder function, right? It receives a message and adds it with plus to the state. So this will only handle integer messages. Now, the function below, we're going to spawn it, and then we're going to send it a string, which is going to cause a crash. It's going to cause a bad arithmetic exception, right? That's not so awesome. We could put an integer guard function in that process there, but that means that any message we send is going to sit in the mailbox of that process forever, right? So eventually your message receives are going to slow down, or you're going to write out of memory, or something like that's going to happen, and nobody's going to have a good time, I don't know, a month from now, right? Here's the exact same actor code in Alpaca. But now what we have is compile time checking of our message flows. So break adder here, the string that we're sending, is going to result in a type error. This code will not proceed to tests, and it will not come out the other side as a beam file. It's not permitted to pass. It is a type error at compile time. And typed message flows in Alpaca revolve around a particular type called receiver. This is what helps us provide typed PIDs, or typed processes. And the keyword receive is what yields this particular type. The message type is the kind of messages that are received by the receive expression, and the return type is the body of the expression, like what comes back from it, right? Here's a very simple example. We have integer messages because the patterns are the messages, right? And we know they're integers because all the patterns have to unify, and there's an integer at the top. And we have string bodies. So this is a receiver of integer messages that yields string values. Pretty straightforward. But what about mixing receivers with other expressions? Because this on its own is not particularly useful, right? So I've boxed the main receiver here in this particular example, right? Remember, receive is the thing that yields a receiver type, okay? Now, X, of course, is also a receiver because X's type is the same type as the expression it's bound to. There's nothing, again, particularly strange there. Now, when we mix X with 1 down here, right, when we combine those things, that whole expression becomes a receiver. The receiver type kind of boxes outside. It re-envelops everything that contains it, right? Unifying a receiver with any other expression moves the receiver to the outside. So the receiver buried all the way down at the bottom of the syntax tree here, right, actually makes the entire enclosing expression a receiver as well. And it means something particular for functions. So what if a function contains a receiver here, right, a receive? Well, the rule still holds. Whenever an expression unifies with a receiver, the entire, including a function, right, the entire expression becomes a receiver. So I'm going to reiterate this a couple of times. When a receive occurs in any expression at all, addition, a function, anything, the whole thing becomes a receiver. The receiver, again, boxes everything that includes it. It smells a little bit like a functor to me, but I'll admit to not digging quite deep enough yet. So what happens when we spawn a function to get a process? And we know that receives are typed, but how does that actually make it to a process or a PID? Well, spawning a function in Alpaca yields a PID, no difference from Erlang there, but for us, a PID is typed. It's generic. The type variable here is the kind of messages that a process can receive. So if you send a message to a PID, the message type you send must unify with the PID's message type. Okay? So we have polymorphic processes, basically, or generic processes in Alpaca. Here at the top, we're receiving integer messages. We know they're integer because we're doing simple addition on them. Right? In the bottom, we're spawning that. So when we actually spawn G here, we get a PID of integers. Pretty straightforward. If we send that process that comes from get a PID of G, if we send that a float, type error at compile time, doesn't proceed to tests, doesn't make it to a beam file. Now, note also in the top right, we have a type here in the function definition, REC. And rec there means that this function types as infinitely recursive. And we specifically include that type so that we can type functions that are written, or type processes that are written the same way as Erlang, where you're looping on a process. If this function ever actually returned a real value, the type would reflect that. But because this function never returns, it has the type of infinitely recursive. What happens if there's no receive? What happens if you spawn a process to do some asynchronous work and you never actually check the mailbox? Well, in that case, we get a PID undefined. A PID undefined cannot be sent messages because undefined unifies with no concrete types. If you try to send an integer to this process here, type error. You try to send it a float, type error. Any message you send to this will result in a type error. You are not permitted in Alpaca to send messages to this process. Undefined will unify with type variables. So if you have like other generic functions, it'll unify, but that just means that undefined is propagated all the way down, and all the way down deep in your call graph, you still can't actually do anything with real values. Okay, let's talk about row polymorphism. In short, our records are intended to be safer than maps with all of the flexibility that matters, or most of it at least. So what on earth is row polymorphism? Well, it solves the problem of information loss. So here we have an identity function for any record that has a field X. This is basic structural pattern matching. Note that we're not checking the type of X here. So this function is actually generic, even with respect to X's type. X could be an integer, could be a float, could be a string, doesn't matter. It could be another record, doesn't matter. Only the presence of X matters. So what's the returned type if we pass a record that has both X and Y to the identity function? Well, without row polymorphism, the ID function doesn't capture the presence of X. This is a little bit like if you use or type with interfaces in Java or C#, right? If you get an interface back from a function, you don't actually have any of the details about the class that's implementing that interface. Your code has forgotten that information. You've lost it. But with row polymorphism, we actually capture it. So it remembers on the other side that there is a Y field as well. If we add fields to a record without matching its type, if we just say this is a record without matching any of its type, we still preserve all of that information out the other side. And because records are immutable in Alpaca, we talk about record transformations rather than record updates. The resulting type of a transformation is distinct from the input type, just as the record itself is distinct from the input type. Right? When we construct with y, it does not affect r there at all. Okay? And as a result, we allow transformations not only to add members, but we also allow them to transform an existing member's type. So at the very bottom here, we're actually replacing the integer x with a string x. And again, because each one of these records is a distinct type and a distinct value, this is perfectly safe. Okay, so in the abstract of my talk, I mentioned a few trade-offs that Alpaca makes, and I'm not going to lie, we do have a few big ones. So the first one is that when it comes from moving processes from Erlang to Alpaca, there's no way to test their parameter type. It's an undecidable problem. So that means that if you get a process or a PID from an FFI call, your message sends are unsafe. Alpaca is going to make its best guess based on what you do with that process, but it might be wrong. There's no actual information there to help Alpaca out. As far as code reloading goes, it's a little bit of a gamble. We have some initial ideas that may be good or bad, mostly around or inspired by things like database migration tools, and checking the types of things. It's probably going to be a tooling problem more than solely a language problem. But it's really just at the idea stage. If you have particular ideas here, we're happy to hear them. So please come help. And lastly, OTP interoperation. We can build typed replacements for things like Gen Supervisor or Gen Server, but real OTP integration is often going to devolve to what's really a typecast. The kinds of things we're talking about can guarantee that things like message types in a Gen Server all line up or reply types all line up. But short of building those things directly into Alpaca, we can't actually prove that the type of a process coming back from spawn link is actually the kind of process that you think it is. Now note that the issue here is about proof. In all likelihood, it is type safe, but we can't prove it. We can't actually provide any guarantees about it, so that's a little bit problematic. Now, the Alpaca compiler itself is actually pretty simple. The front end contains all the basic lexing and parsing. We use leaks and yek. It's just part of the standard Erlang distribution, so there's no strange new tools involved at all. Lots of good examples out there in the community. I based a lot of the stuff initially with leaks based on examples from LFE, right? So there's lots of documentation out there. I tend to think of the AST generation stage as distinct from the front end. It does perform a little bit of trivial validation, but most of its job is rolling up different function versions into one concrete one. So this is when you're doing pattern matches in functions, in the function heads, excuse me. And it does a bunch of variable renaming as well. So this prevents things like variable leaking from a receive block, or making sure that things like multiple wildcards are properly named for core Erlang, that kind of stuff. Pretty straightforward. It should be noted that everything after Alpaca's AST generation stage works on our AST. We don't have an intermediate language, we just operate on the AST. So code generation turns our AST into the core Erlang AST and then just runs the core Erlang compiler on it directly. The last code generation stage also renames our modules to keep us from colliding with anything within the ecosystem. So if you have a strings module in Alpaca, it will get renamed to Alpaca strings, and all of the internal references and external references in your Alpaca code will be renamed accordingly as well, just to be safe. And as we're wrapping this up, I want to talk a little bit about our community and how it runs. When Alpaca originally became open source as ML-flavored Erlang, it was pretty important to me to ensure that we had a solid grounding in both openness and inclusivity. So to that end, we adopted the Contributor Code of Conduct version 1.4 right away. So any project you see hosted under the Alpaca Lang GitHub organization abides by this code of conduct. And while our community is actually pretty small, it is growing, and I'm really, really grateful for it. As Alpaca started to look like it might actually be viable, the community aspect started to become very, very important. It's virtually impossible for a single person to know every good idea or to be aware of every good idea, let alone for that one person to implement everything. So for Alpaca to become useful, we need a community. It's not going to happen without that. And I mentioned also much earlier that I want to be able to share, the competitive edge that I think this combination of testing and typing capabilities brings. And if that's really a value of the Alpaca community, then we need to make Alpaca itself accessible. To me, this means doing things like, even just the initial things like internationalizing error messages, making the parser pluggable, very, very important things. We actually have internationalization of error messages in our master branch now. So if you want to translate Alpaca's error messages to your favorite language, you just have to edit a PO file. You don't have to edit any code at all in Alpaca whatsoever. The parser itself is pretty pluggable as well. You could write any parser that sits in front of the AST generation stage, and you get everything behind that for free. And as for growing the community, I take a lot of inspiration from a friend of mine in Vancouver named Sim Ghani. Sim was one of the co-founders of a Vancouver-based meetup called Polyglot. Polyglot's both a meetup and an unconference. The unconference yearly sees 300 or so people. There's regular meetups that see a couple hundred people and regular social meetups as well and hack nights. And it's a community that's predicated on the kind of openness and inclusivity that I really value and exhibits a lot of the characteristics that I'd like to see fostered within the Alpaca community too. When Simon and I were talking about the genesis of the Polyglot meetup a few years ago, he told me that he got behind it initially as he saw it as a way to build the kind of both personal and professional support group that he wanted to have. And I'd like to see Alpaca be that same thing. It can be hard to find a group of compiler hackers to hang out with and ask questions and learn from, and I'd like to be able to provide that for other people. And ultimately, a big part of what excites me about our growing community is being able to learn more. The ideas that other people are going to bring to Alpaca will make our community much richer and make the tool much more robust as well. The community itself right now mostly communicates via GitHub issues and pull requests. The IRC channel is sporadically active, and the mailing list is very young. We've used it mostly to announce releases or coordinate some bigger picture ideas. But please come join us in all or any of these forums at your convenience. As far as where to help us out, literally anywhere. There's a huge wide open space now, so if you want to come and leave sort of your imprint, your ideas in the concrete of Alpaca, by all means come talk to us, anytime, anyway, here too. We have a number of community projects that are already useful. A Rebar 3 plugin, so that makes it fairly easy to get going with Alpaca right away and mix both Alpaca and Erlang code from the get-go. There's a simple shell that's actually bundled with the Rebar 3 plugin, so it's like a very basic REPL that it's in early stages. There's a simple Emacs mode that did all the syntax highlighting for all of the stuff that you saw so far, and a Visual Studio Code integration too. It's all in the early stages, but everything shows a lot of promise, and again, is pretty useful right away. We're starting to sketch out the beginnings of a standard library too. There's one module in it so far, and haven't really settled on how that's going to be available for projects that use the plugin yet, the Rebar 3 plugin. So there's a lot of room for ideas there too. Tooling is really a wide open area right now, especially too with respect to how we output and organize documentation. We don't have solutions for that yet. It's really still so early that we can use your help literally anywhere. Simple and really excellent places to start are writing examples for other people to follow along with, or write library bindings with our FFI to make other things immediately useful. Joining documentation efforts, or just helping us direct sort of the course of inquiry and ideas and finding new directions are all really, really valuable ways to participate. Or just use it and break it. Please find some bugs. There are lots there under the hood, I'm sure. We really would love to have more participation in every and any aspect of the community, including compiler development. If you want to get into the guts of the typer and want a guided tour, I'm happy to do that too. I'm personally pretty interested in getting Alpaca self-hosted and in writing a code formatter in Alpaca directly, but we do have a bit of a distance to go yet before we're there. And finally, just to close this out, I wanted to give you a few links, and these will be in the slides that are available shortly as well. We have a basic language tour in the GitHub repo, so you can see in a bit more detail all of the features and functionality that's there, including binaries and all that stuff. The typer started from a Oleg Kiselyov post on how the OCaml type checker works. In fact, the very first version of our typer was almost a literal port of his OCaml code to Erlang, and then we just expanded from there. And the last one there is a great presentation on row polymorphism if you want to get into the guts of how things like field addition and removal work. We don't actually support removal right now, but it's a thing that we could talk about. And with that, thanks for coming, and I'm happy to take questions. We got a few hands. I'll let the guy with the mic pick where we're going first.
I wonder if you know about PureScript and that somebody was working on a PureScript, on a Beam backend
Yeah.
for it, and why both?
That's a great question. I actually became aware of that after the first open sourcing of what Alpaca was. It looks really neat. They actually, I think, do some, I haven't looked in a ton of detail, but they do some similar bits around, I think they have a similar idea to receivers. Not exactly the same, but there's some similar tracking. It's really neat. It uses PureScript's FFI, and yeah, right, like that standard thing, which is fine, but I wanted something that was a little bit more directly compatible with Erlang as well. A big part of this is I wanted it to be buildable in Erlang so that we could just kind of bootstrap there and get up and running right away. Yeah, but it's a super neat effort. I'm really curious to see where they go with it. Yeah.
Hey, I'm wondering if you considered in the development an approach similar to TypeScript where you're essentially adding types as a transpilation stage, and then compiling down to either Erlang or Elixir, and why if you considered it, and why you didn't approach that.
Sure. I'm not super familiar with TypeScript, so I'll try to answer your question effectively, and you can correct me if I get off course. As I understand it, TypeScript is sort of bolting annotations onto JavaScript. Is that about right?
Yes.
Okay.
Including with like type inference and stuff, but
right.
Yeah, I mean obviously the advantage being that you are then compiling to the language that everyone already knows and also
yes.
the ecosystem.
Yeah. I will admit to being a bit of a language zealot in some ways there and wanting the expressiveness of ML. Yeah. Well, yeah, there's a certain sort of expressiveness that I think case classes bring specifically, and records and type constructors feel close enough to me that I wanted that kind of thing. We can approximate that in Erlang, of course, right, with tuples and such, but I wanted a little bit terser, briefer kind of thing happening. So there's definitely a bit of a desire to be slightly obtuse there, I'll admit to that. Yeah.
I just want to say that I've been following since the MLFE days.
Oh, cool.
This is the coolest new project ever. So,
thanks.
I want to ask what's the type class story?
Sure.
Are you thinking about that? How do you, because there's this whole generic module extension to SML that's out there somewhere, and there's type classes.
Yeah.
Where would you like to go with this?
That's an excellent question. I'll give you two answers. The short answer is I don't know. The slightly longer answer is I think the thing that I'm most enthusiastic about right now is Trait's approach similar to Rust. Type classes are nice. I have some negative experience in Scala with implicits and the implicit conversions and things that makes things a little mysterious sometimes, and so I want to kind of stay away from as much magic as possible. Although we are talking about things like the OCaml implicit modules paper. That's come up a couple of times. Straight type classes like Haskell's are an interesting approach as well, and I think relatively similar in some ways to traits. So if you have particular ideas, I'd really encourage you to come hang out and talk about them. It's something that keeps popping up here and there, and I think it's going to couple with how we approach something like a gen server, right? Because we need to generate a module from a set of functions. Yeah, I think it's going to look something like traits and row polymorphism with records, like something in the middle there, and I just don't know yet, to be honest. I hope that's not an unsatisfactory answer. Okay, cool.
Okay, thank you. I don't think we have time for more questions.
Okay.
Maybe one more. Okay, last one. Yeah.
You can feel free to come bug me anywhere today as well, but
okay.
Yeah.
So now that I have the mic, I have two questions.
Please.
The first one is, it seems like the FFI is basically annotating external functions with types. That's sort of what it's doing behind the scenes. So are you collecting those annotations anywhere? Is there like a repo that I can go to so that I don't have to annotate all of Cowboy?
Yeah. So the annotations are actually restricted to Erlang guard functions. So you can only use the primitive type annotations. So Cowboy specifically is an interesting case because I actually have a bunch of Cowboy code deployed at work. And I think we probably need to talk about something like a more opaque bridge, like some sort of opaque type, where we say, I want you to call this function in this module, and I'm going to assert that this is the type, like some arbitrary name, like a Cowboy request, right? Like, how do we type that, right? Maybe that's sort of the example. And in that case, then we might have additional restrictions like, well, you can have these opaque types, but if you have them, you can't put them in a union, right? You have to use them standalone. That's not necessarily desirable. But we're probably that's a potential angle. The only other way really to do this with Cowboy is to say, well, we're going to destructure the tuples, right, in the FFI and kind of get nasty that way. But yeah, we're limited to the guard functions in Erlang because we actually compile those, we output those guard functions in the core Erlang directly. Because we want the runtime checking and the compile time checking. Does that make sense?
Yes.
Okay. Is that it?
The question was,
yeah.
Just giving your code, it looks like this is all written in Erlang. So what's the plan on changing that to Alpaca?
Yeah, in master, you'll note that there are a few AST nodes that are now defined in Alpaca directly. So things like function names, variable names, those are considered a symbol in the lexer and the parser. And symbols actually now are defined in Alpaca as a type constructor and row polymorphic record. So I think it's going to be sort of a gradual process, although I was talking with Tristan about the Rebar 3 plugin, and I think I might have painted us into a corner in terms of bootstrapping there. So I might have backed that back out. I think it is going to be a gradual process, probably starting with the AST and then replacing bits as we see opportunities. If you look at the typer code, it's about 6,000 lines, including tests, and a lot of nested pattern matches. So there's a lot of opportunity there for us to simplify things. I hope that's a satisfactory answer. I know it's not very direct, but we don't have a really clear plan yet. It's going to be sort of piecemeal and seeing which bits are easiest to bootstrap first. Yeah.
Okay, time stamp for the beat. Let's thanks.
Thanks.